In this video, I'm going to talk about scalars and vectors. In physics, we come across a lot of measurable quantities, and these measurable quantities can be broken down into either scalars or vectors. At the beginning, I'm going to talk about scalars. Scalar is a quantity that can be completely described by its size, or what we call its magnitude. For example, mass, time, temperature, volume, those are all examples for scalars. Applying algebraic rules for scalars is straightforward. For example, if you have, let's say, 3 kilograms, so I'm taking an example from mass. If you add 5 kilograms to this, then the answer is 8 kilograms. For example, you have 10 kilograms and you subtract 5 kilograms from that, and then the answer is 5 kilograms. How about multiplying scalars? Let's say you have 10 seconds multiplied by 15 seconds. So then your answer is 150, and the units would be second square. Let's say you have you are going to take a division between temperatures. You have 250 Kelvin divided by 25 Kelvin. So then the kelvins in the numerator and the denominator cancels out, and you are going to get just a number 10, and that is unitless. So when we have scalars, the algebraic rules are very straightforward, very simple. However, vectors on the other hand are very different. Applying the algebraic rules are not straightforward for vectors. So that's why studying them are very interesting. A vector, by definition, is a physical quantity, a measurable quantity that can be described by two things. One, the magnitude, or what we call the size of that measurable quantity, and its direction, the direction of the measurable quantity. For example, we will come across so many vectors in our course. To start with, displacement, velocity, acceleration, any type of force, electric field, magnetic field are some of the vectors that we are going to discuss throughout this course. Okay, now let's look at how to represent a vector. First, let's see how we represent them symbolically. We use a letter, and on top of that letter, we put an arrow. So it could be a lowercase letter like this, or even it can be like uppercase letters. So if you see this notation, then you know that you are dealing with a vector quantity. Sometimes instead of writing the arrow, we even put a tiny bar on top of a letter. So then again, it symbolizes a vector. So keep that in mind. That's how we represent a vector. So this is method 1. Method 2 is, instead of putting an arrow or a bar on top of the letter, we make the letter boldface. However, when we write, it is very hard to write bold letters. So in writing, we ignore this method. But still, in textbooks, you'll see that if you see a bold face print, then that usually represents a vector quantity. So this is how we represent vectors symbolically. Graphically, a vector can be represented by an arrow. A vector has a magnitude as well as a direction. So the magnitude of the vector is represented by the length of the arrow. So that is the distance from the tail of the arrow to the head of the arrow. The direction of the vector is represented by the arrowhead. the arrowhead is pointing in a certain direction relative to space, and that's the direction of that particular vector. Now I'm drawing this dashed line, kind of an extension to the actual vector. This dashed line shows the line of action for this particular vector. So this is called the line of action. Especially when we deal with forces later on, which is a vector quantity, you will see that we are mostly interested in what is the line of action of a force, along with the magnitude of the force and the direction of the force. Sometimes symbolically, the magnitude or the size of a vector is represented like this. Now you know how to symbolically represent a vector quantity. The magnitude of this vector is given by the modulus of that vector. So whenever you see these two parallel lines, that's taking the magnitude, or what we call the modulus. Okay, now let's talk about equal vectors. If vectors are of the same kind, they have the same magnitude and the same direction, then we call those vectors equal vectors. For example, let's say we have two 5 Newton forces pointing in the same direction. So 5 newtons is the size. So each vector will have the same length, because 5 newtons represents the size of the vector. They are in the same direction. You can see the arrowheads are pointing in the same direction. And also these vectors are of the same kind. They are forces. So as a result, we can say that these vectors are equal vectors. Now let's look at this example where we have a 7 meter displacement vector and a 7 Newton force. As you can see, the lengths of these arrows are the same, representing that the magnitudes are the same, 7. Their directions are also the same, that is the direction of the arrow that points in the same direction. However, the first vector is a displacement vector. The second vector is a force. So they are not of the same kind. Even though the magnitudes of the vectors are the same, the directions of the vectors are the same, since they are not of the same kind, these are not equal vectors. However, the first example that I showed you, they are equal vectors because they are of the same kind, their magnitudes are the same, and their directions are the same. All three conditions need to get satisfied if we want to have equal vectors. Now let's look what happens when we multiply a vector by a scalar. A scalar is simply a number. It can be either positive or negative, but it's simply a number. You just have a magnitude. There's no direction defined for a scalar. So let's say our scalar is k, and initially it's greater than 0, that is, it's a positive value. So let's consider our original vector as a, and then I'm going to multiply by 0.5. So let's say k is 0.5, so we have 0.5 times a. Then you can see the vector becomes half. That means its size is halved, but it's in the same direction. So the direction does not change when we multiply by a positive scalar value. If we multiply it by 2, then the vector doubles. like this. So this is 2 times A. If we multiply it by 3, then it's going to be 3 times A. So this is what happens when we multiply a vector by a scalar. If the scalar is positive, then only the magnitude of the vector changes, keeping the direction constant. The second case is when k equals 0. So that means we multiply our vector by 0. So then we are going to get 0 vector. So this is called the 0 vector or the null vector. In this case, the magnitude of the vector is 0. The direction of the vector is undefined. It's not defined. So this is a special type of a vector, what we call the 0 vector. So that happens when the scalar is 0. Then the third case is when k is a negative value. So that means k is less than 0. So let's say that we multiply the scalar by k equals negative 0.5, like this. So our vector is negative 0.5 times a. Then the vector, the new vector will have half the magnitude, but it's pointing in the opposite direction. So the direction reverses when we multiply by a negative number. So for example, negative 2 times a will mean the vector is twice the length, but it's pointing in the opposite direction. Now let's talk about another special case. Again, k is less than 0 and k is equal to negative 1. So let me draw our original vector, vector A, pointing in this direction. In order to apply this special case, I am going to multiply the A vector by negative 1. As a result, the new vector is going to be negative A vector. Negative A vector has the same size as the original vector, but its direction is completely reversed. So that's the importance of this vector. So the pair A vector and negative A vector, if they are of the same kind, that is, you have the same magnitudes, they are reverse, they are opposite in direction, but they are same kind vectors. Let's say they could be force vectors, they could be displacement vectors, they could be velocity vectors. If that's the case, then we say that these are opposite vectors. Earlier we talked about equal vectors. This time we have opposite vectors. So if we take the vector sum of the opposite vectors, that is this sum, we can also simplify this as vector A minus vector A. We end up with the null vector or the 0 vector. So this is another way to get the null vector. You can multiply a vector by 0, then you get the null vector, or you can add opposite vectors. Vectors that are of the same kind, they have the same magnitude, but they are in opposite directions. Their directions are reversed, and when you take the vector sum of those vectors, you get the null vector. So these sums are called vector sums. So in my next slide, I'm going to talk more about these vector sums. Before talking about vector sums, I'd like to point out a very important property of vectors. That is, a vector will not change if it is slid parallel to itself. That means you can slide a vector without changing the vector, because the process of sliding is not going to change its direction nor its magnitude. So as an example, if we consider vector A, this is vector A, I'm going to slide this vector parallel to itself. So this is the original position, and after sliding, it will be somewhere over here. That's the same vector A. So I have slid the vector in this direction, and it's the same original vector. Only the line of action has changed. Originally, the line of action for the vector is here, but now the line of action is over here. Let's look at another example. I'm going to draw vector B like this, and again I'm going to slide this vector. So these dashed lines, I'm drawing these dashed lines as guidelines to correctly slide the vector, and after sliding, the vector is over here. You can see its direction is the same, its size is the same, but the line of action has changed. But that's not going to change the vector. So this is the same vector. Another position, let's say that I'm going to slide the vector like this. To this position. And again, it's the same vector. So keep in mind this very important property of vectors. A vector will not change if it is slid parallel to itself. So keep this in mind. This is going to be important when we talk about vector sums. Okay, now we are going to talk about how to obtain the vector sum of vectors. There are three main methods to do it. First, we are going to talk about the graphical method. Let's consider two vectors. We'll start with two vectors. This is vector A, and then we have a vector B like this. I want to take the vector sum of this. Now remember, this is not a normal sum, like sum of two numbers, because as you know, a vector has a size as well as a direction. So when we are doing a vector sum, we have to consider two things, that is the size of those vectors as well as their directions. So in the graphical method, what we do is that we connect the head of one vector to the tail of the other vector. So that's where sliding vectors are very important. I'm going to, for example, let's say that this is a vector B. I'm going to slide vector A such that its head connects with the tail of vector B. That's why understanding sliding a vector is very important, and the fact that it's not going to change the vector, the process of sliding. That's important when we do the graphical method of vector sum. So now how do we find the vector sum? Simply you connect the free ends of these two vectors. I'm going to connect the tail of vector A to the head of vector B. And then the length of that side and its orientation in space will give me the vector sum AB. So this is vector sum A vector plus B vector. Sometimes this is also called the R vector or the resultant vector. I'm going to talk about this in detail, but I just want to explain it under this slide. The second method, which is the more commonly used method, is the trigonometric method. That means when you get a vector, again I'll call it vector A, what you are going to do is that you are going to construct a right angle triangle keeping that vector on the hypotenuse, like that, and say that you identify this angle. Then you can find perpendicular components of this vector. We call this decomposing this vector into its perpendicular components. That is what is meant by this trigonometric method. So if you remember trigonometric functions, this side can be given as a sine theta, and this side can be given as a cosine theta. And if you have many vectors, two vectors or more, you apply this method to all those vectors and you are going to get vertical components and horizontal components. You add the vertical components together, then you add the horizontal components together, and you eventually find the vector sum or the resultant vector. So this method is the trigonometric method, and that's the method we are mainly going to use in our courses. Again, this is just a brief explanation. I'm going to explain these things in detail later on in this video. The third method is the unit vector method. So this method is not discussed in college physics courses, but mainly it's discussed in calculus-based courses like general physics courses. Here we are going to represent a vector in terms of its unit vectors. Now, unit vectors are vectors of magnitude 1 in the direction of x-axis and the y-axis. And if there's a z-axis, you can also define a vector along that direction. For example, along the positive x-axis, we define the unit vector as I hat. So that symbol on top of I is called the hat. Along the positive y direction, we define a unit vector called j hat. So what we do is that we represent any given vector in terms of I and j's, and then when we need to get the vector sum of many vectors, we simply add all the I components and all the j components of those vectors, and we get the vector sum. So again, remember, this unit vector method is discussed mainly in general physics courses, not in college physics courses. Now let's try to use the graphical method to add or subtract vectors so that we end up with the vector sum. One important thing is that when you add or subtract vectors, they should be of the same kind. For example, we can only add or subtract force vectors with force vectors, or displacement vectors with displacement vectors. We cannot add or subtract, for example, force vectors with momentum vectors, force vectors with velocity vectors. That's not possible. So always remember, the vectors should be of the same kind. Now suppose vector A and vector B are of the same kind. So what is the process of adding these two vectors? We arrange vector A such that its head, that is this point, connects with the tail of vector B. So that's where, as I told you earlier, sliding of the vector comes into the picture. So we have to slide vector A such that its head nicely fits the tail of vector B. So simply you slide the vector A like that, And this process does not change vector A. And that's how you do it. This method, this arrangement is what we call the head-to-tail arrangement of vectors. So in a way, you are joining the two vectors, and then this is the result. So how do you find the vector sum? You connect the tail of vector A, tail of the first vector, with the head of the last vector, in this case vector B, because we only have two vectors. So like that. And this vector is what we call the resultant vector. It's called the resultant vector, and R is equal to A vector plus B vector, and this is the vector sum of the two vectors. So that's how we get the resultant vector. The direction of the resultant vector gives the direction of the sum. The magnitude or the length of the resultant vector give you the magnitude of the vector sum. So this is a very simple method to find the vector sum. However, since we have to graphically draw vectors, connect them, that takes time, and as a result we rarely use this method to find the resultant vector. Now in this example we have 6 vectors. So again we can use the head to tail arrangement of vectors to find the vector sum of these 6 vectors. So I'm going to start with vector A. I'm going to slide the vector such that it looks like this. So that's vector A. And then I'm going to slide vector B so that the tail of vector B connects the head of vector A. So where we stop A, that's the place we start with vector B, and its orientation, when we slide it, we conserve its direction and its size. So then it will look like this. So that's vector B. And then we'll slide vector C in place. So it will be like that. So that's vector C. And then joining the head of vector C would be the tail of vector D, which is in this direction. So that's vector D. And then we have vector E. Again, you can slide that vector so that you preserve its direction and size. And then finally you have vector F. Again, when you slide it, it's going to look like that. So I'm drawing these approximately, but you get the idea. If you are doing this correctly, then you need to have some sort of a scale. So that means, let's say that these are, for example, force vectors. So then you should have a scale like 1 Newton is represented by 1 centimeter. And then you exactly, if it's 5 newtons, then you represent that by 5 centimeter length arrow. And in order to find the direction, you need to have a protractor. So then you get these angles using the protractor. So that's why this graphical method is very tedious, because you need to be very specific with the lengths, have a scale, you need a protractor to exactly measure these angles relative to some axis. So that's why it's very time consuming, and we rarely use this method to find the vector sum or the resultant vector. Okay, now let's try to find the vector sum or the resultant vector for these six vectors. For that, we simply connect the start point of the first vector, that is vector A, to the end point of the final vector, that is the head of a vector F. So it's going to be a straight line like that, and that will give the resultant vector that we need. Its direction and its length will give us the size and the direction of the resultant vector. Now you can apply the previously discussed vector sum of two vectors to get the resultant vector as an equation. For example, if you can see A vector and B vector, so if you think about these two vectors, that gives you the vector sum for those two vectors, A vector plus B vector. Then you can add that result to vector C. So that is this one. So now you have another triangle, and that the sum of that would be A vector plus B vector plus C vector. And then you have the other one, A plus B plus C, added vectorially to vector D. So then you have this one. And that sum would be vector A plus vector B plus vector C plus vector D. And for that sum, you are going to add vector E. So that is this. From this triangle, you get that result. So you will have vector A plus vector B plus vector C plus vector D and plus vector E. And then finally, that sum is added with vector F vectorially, and you get the resultant R. So you should be able to see that the resultant vector R is simply A vector plus B vector plus C vector plus D vector plus E vector plus F vector. So that's a mathematical relationship for the resultant vector. This gives you the graphical way of explaining it. This entire configuration is what we call a vector polygon. And in some cases, we use this method to find the resultant vector. However, as I told you before, this is time consuming, so that's why we use a trigonometric method to simplify these vectors in order to get the resultant vector or the vector sum. Now, how do we subtract vectors using the graphical method? So here again we have vector A and vector B. Now we need to find the difference between the two vectors, vector A and vector B. As you can see, the minus sign can be rewritten using this method. That is vector A plus vector minus B. So instead of B vector, now we need the minus B vector. So if you know the B vector, in order to get the minus B vector, you simply multiply it by -1, which will make vector B to completely reverse itself. So then we'll have negative B vector in this direction. Relative to B vector, its direction is completely reversed. Now what you're going to do is that you're going to slide vector A such that its head connects with the tail of vector minus B. So like this. And that's your vector A. So then the resultant or the vector sum is obtained by connecting the tail of vector A with the head of vector minus b. So here you can see that result. The blue arrow shows you the difference between vectors a and vector b. So this is a vector difference, and that's how you get the answer. So again, remember, even if you have a difference of two vectors like this, you can write it as a vector sum of a positive vector and a negative vector like this. Okay, let's try to do example 1 where we need to find the resultant vector r of the following three vectors that are exerted at point P. We are going to use the graphical method to get the resultant vector. So here I'm going to slide vector A to a position, let's say somewhere here, and I'm trying to get the same length for vector A. So that's my vector A. And then I'm going to slide vector B so that its tail is connected with the head of vector A. So I'm using the head to tail arrangement here. So like that. So that's my vector B. And I'm going to slide vector C to the position of vector B. Like that. And that's my vector C. Now, if I want to, so let me label them. So this is my vector A, this is my vector B, and then this is my vector C. And the resultant vector is obtained by connecting the free ends, that is the tail of vector A to the head of vector C. So I'm going to use a different color for that. So let me use red color for that. And then this will give me the resultant vector R. So that's my vector R. So in a mathematical way, I can write this relationship as the resultant vector R is equal to the vector sum of A vector, B vector, and C vector. So this is how you use the head to tail arrangement to figure out the resultant vector or the vector sum of these three vectors that are exerted at point P. Okay, now let's look at example number 2. Here we have four vectors. Again, using the graphical method, we can find the vector sum or the resultant vector. However, there's more information given. It says that vector A, the magnitude of vector A is equal to the magnitude of vector C, and the magnitude of vector B is equal to the magnitude of vector D. So with this information, we can start plotting the vector polygon. I'll start with vector A. I'll slide it to a place like this. And then I'm going to connect the tail of vector B to the head of vector A. So like this. So that's vector B. And then I'm going to connect the tail of vector C to the head of vector B. Like that. And then finally I'm going to connect the tail of vector D to the head of vector C. Like that. And you can see in this particular case, when we create the vector polygon, it completes the vector polygon, meaning that we cannot find free ends of vectors. It's basically complete the polygon. So let me again label the vector. So this is our vector A, this is our vector B, this is our vector C, and this is our vector D. So what does this mean is that the resultant vector is equal to the 0 vector. So whenever you have a vector polygon completing itself, that means there's no resultant vector. The vector sum is equal to 0. So we can show this mathematically. Again, what I'm going to do is I'm going to write down the vector sum, including all vectors. Vector A plus vector B plus vector C plus vector D. However, if you look at this information, you can see vector A and vector C, they have the same magnitude, and from the drawing here, vector A and vector C are opposite to one another. So that means vector A is equal to negative vector C. In a similar way, we can find that vector B is equal to the negative of vector D. So in other words, vector A, C and vector B, D are opposite vectors. So with that, we can rewrite this expression over here, vector A plus vector B, and instead of vector C, I'm going to substitute vector minus A. And for vector D, I'm going to substitute vector minus B. So now you can put A vector and minus A vector together, and B vector and minus B vector together, and you can see the result is the 0 vector. So mathematically, we have proven that the vector sum for these four vectors is 0, the null vector or the 0 vector. The other way is when you geometrically do the drawing of the vector polygon, if all the sides close and create a closed polygon, that again tells you that the resultant vector or the vector sum is 0. Now let's look at the trigonometric method of finding the vector sum or the resultant vector. There are two important skills that you need to perfect when using the trigonometric method. The first skill is, given a vector, how do you find its perpendicular components? So this is one place where we are going to use trigonometric functions. The second skill is the reverse of skill 1. That is, given the perpendicular vector components, how do you find the resultant vector? So remember, whenever you are dealing with a vector, determining a vector means finding the size of the vector or its magnitude as well as the direction. There are two things involved. So that's skill 2. It's basically the reverse of skill 1. Now let's try to understand how to apply skill 1, that is, given a vector, how do you find its perpendicular components? Here I am representing a vector A that makes an angle theta with the positive x-axis. You can see the positive x-axis is to the right. Then the positive y-axis is in the upward direction. This is the normal convention when we draw the xy coordinate system. And you can see the A vector is in the first quadrant. Now, the first step, as I told you, is to identify the x and y coordinate systems. Then, the second step is to identify where the angle is. So here, the angle is over here and it makes a theta with the x-axis. Third one is to create a right angle triangle where the length or the size of the vector size of vector A is the hypotenuse, of the right angle triangle. So this is very important. Now the two sides of the right angle triangle. So first I'm going to represent the side along the x direction or the positive x direction. So that's this vector. And then the side along the positive y direction. So that's represented by this vector over here. Now let me label these vectors AX vector and a y vector. You can clearly see that ax vector and ay vector are arranged head to tail along this the sides of the right angle triangle. So as a result, I can write a vector is equal to the vector sum of ax vector plus ay vector. Now our objective is to figure out ax vector and ay vector in terms of the angles, the trigonometric functions, and the original vector A. So let's see how we can do that. I'm going to first use the definition of cosine theta. If you recall, that's the adjacent side of the right angle triangle divided by the hypotenuse of the right angle triangle. Now the adjacent side is this side. So that means the length of this side, which is basically the magnitude of the ax vector. Hypotenuse is this longer side of the right angle triangle, and that is given by the magnitude of the a vector. So from here we can say that the magnitude of the ax vector is equal to the magnitude of the a vector times cosine theta. Now this gives the magnitude of the ax vector. Now if you want to represent it as a vector, the magnitude and the direction is important. But you can see the direction of ax vector is in the positive direction. So I can simply write this as ax vector is equal to positive a vector times cosine theta. We usually don't write the positive sign, but however, to represent the direction of ax vector, I'll just put the positive sign so that it's clear at the very beginning of this explanation. Now similarly, I'm going to consider the sine theta, the definition of sine theta. So that's the opposite side divided by the hypotenuse. So again, just like the previous case, it's going to be the magnitude of the ay vector over the magnitude of the a vector, and you'll see that ay vector, magnitude of ay vector is the magnitude of a vector times the sine theta function. And as a vector, I can represent ay vector positive. Why it's positive? Because you can see the vector ay is aligned in the positive y direction. So a sine theta. So that's how you get the component vectors for this vector A in the first quadrant. I have given you the magnitudes, the way to find the magnitudes of those component vectors, and the direction of those component vectors are simply, you can use the definition of your coordinate system. So that's how you do this for the first quadrant. Now let's look at what happens if the same vector is in the second quadrant. So just like in the previous case, we have to first identify the coordinate system. We have the negative x direction and the positive y direction. The angle theta is again measured relative to the x-axis, and this is the vector A. So what we do is that we define a right angle triangle where the magnitude of the vector A represents the hypotenuse of the right angle triangle, and the sides of the right angle triangle are represented by the component vectors, that is a component vector along the negative x direction like this, and the other component along the positive y direction like this. And I'm going to label them as ax vector and ay vector. Just like in the previous case, you can see from the head to tail arrangement of these component vectors, we can get a vector is equal to the vector sum of ax vector plus ay vector. Now, again using the cosine theta and the sine theta, their definitions. I'm not going to write the definition adjacent over hypotenuse. I'll simply write the magnitude of a x vector over the magnitude of the a vector, and that will give me the magnitude of the ax vector is equal to magnitude of the a vector times cosine theta. Now, if you look at the direction is along the negative x direction for ax vector. So, as a vector, then ax vector can be given as negative a vector times cosine theta. The negative sign comes because it's along the negative x-axis, not the positive x-axis. Now, from the definition of sine theta, we can get the magnitude of the ay vector in this way. So, magnitude of ay vector is equal to magnitude of the a vector times sine theta. Simply, you have to refer to the right angle triangle, look at the sides, and then obtain this result. So in terms of a vector, if you want to write a y vector, that's going to be equal to plus a vector times sine theta. Why it's plus? That's because the ay vector is aligned or along the y direction, the positive y direction. That's the reason that I put a plus sign here. Next, we'll consider a vector in the third quadrant. So identify the x and y direction. So here you can see the x is actually along the negative x direction. Y is along the negative y direction. So those are our directions. The angle theta is measured relative to the x-axis, the horizontal axis, and this is our vector. Then the important thing, you construct a right angle triangle keeping the magnitude of the vector as the hypotenuse. Then the other two sides are represented by the component vectors. One component vector along the negative x direction like this. Then the other component vector along the negative y direction like this. And let me label those vectors, component vectors, ax vector and ay vector. Again, from the head to tail arrangement, you can clearly see that a vector, the vector sum of a vector is simply ax vector plus ay vector. Just like in the previous case, our objective is to find the magnitudes of ax and ay and their direction. The directions are obvious, but how do we find the magnitudes? We use the definition of cosine theta and sine theta. Cosine theta can be defined as the magnitude of ax vector over the a vector. So then magnitude of ax vector is equal to magnitude of a vector times cosine theta. Now, if you think about the direction, this is the magnitude, the direction is along the negative x direction. So vector ax can be written as negative vector a times cosine theta. Now for the ay vector, we are going to use the definition of sine theta, magnitude of the ay vector over the magnitude of the a vector, and just like in the previous case, we can find magnitude of ay is equal to magnitude of the a vector times the sine theta. Now, as a vector, we need magnitude and the direction. Uh, just like in with ax, ay is pointing in the negative xy direction. So as a result, we have to put the negative sign a vector times sine theta. So this is how we represent the component vectors in the third quadrant. Finally, we look at a vector in the fourth quadrant. Again, identify the x and y coordinates. So x is the positive x direction, y is the negative y direction. The angle is measured relative to the x-axis, and as you can see, the vector is oriented in the fourth quadrant. The important thing, as mentioned earlier, we have to construct a right angle triangle by keeping the magnitude of vector A as the hypotenuse. So then the component vectors will represent the two sides of the right angle triangle, just like this one. So this component vector represents the positive x direction, and then this component vector represents the negative y direction. And let me label those vector components. This is my ax component, and this would be my ay component. And now you should be able to clearly, very quickly figure out what is ax vector and what is ay vector, even without going through the definition of the trigonometric functions. However, I will still write that down because this is the initial stages of learning this material. So we have ax vector, a magnitude of that divided by a vector, and as a result we'll get the magnitude of the ax vector as the magnitude of a vector times the cosine theta. But if we look at the vector ax, then it will be plus vector a times its cosine component. From the sine theta definition, we'll get the magnitude of ay vector over magnitude of the a vector, and in a similar way, we'll get magnitude of ay as magnitude of a vector times the sine component, sine theta. But remember, if you represent vector ay, then it will be negative because that vector is pointing along the negative y direction. So you'll remember to put the negative y, negative sign. You'll have vector a times the sine theta. So that's how you represent the component vectors if the vector is aligned in the fourth quadrant. Now let's summarize the component vectors that we got for each quadrant. For the first quadrant, x component vector of a, so that can be written as a cosine theta. The y component a sine theta, and both are positive. For the second quadrant, the x component is negative, so minus a cosine theta, but the y component is positive, a sine theta. For the third quadrant, both components are negative. That is, the x component, that's negative, as well as the y component, that's also negative. And finally, for the fourth quadrant, the x component is positive, a cosine theta, but the y component is negative with a minus a sine theta. So it's a good, this table is a good way to remember those things, but I want to caution that there are some exceptions to this. For example, note 1, you can see the right hand side, this is valid if the right hand side is considered positive and the upward direction is considered positive. So to begin with, that's what we did with the xy coordinate system. You had the y-axis and then you had the x-axis. We considered this side as positive and this side as positive. So then the downward direction is the negative direction and the left hand side direction is again the negative direction, that is along the x-axis. So, so this table is valid when you have this convention for the xy coordinate system, and that is the most normal situation. Now let's look at another very important note. Don't always think that the x component is given by the cosine term. So this is, most of the time students think that, okay, if it's the x component, it's cosine. If it's the y component, then it's the sine component. Again, don't think it in that way, because there are exceptions. As I'm showing you here, this particular example. Again, you can see the vector A, it lies in the first quadrant. You have the positive x direction and the positive y direction. So you identify the xy directions. Then when you look at the angle, you can see theta is not relative to the x-axis. In this case, theta is relative to the y-axis. Okay, so we also identify that. And the third one is you have to construct a right angle where the magnitude of the vector represents the hypotenuse of the right angle and the remaining two sides represents the y direction and the x direction. So in that sense, I'm going to draw the component vectors like this. So I'll draw a component vector like that representing the y direction like that, and then this vector component representing the x direction like that. And now let me label those vector components. So this is my ay vector component and this is my ax vector component. Now if you look carefully, what is cosine theta? The definition of cosine theta is adjacent over hypotenuse, the magnitudes. So the adjacent in this case, for this particular right angle triangle, is not our usual ax, but it's ay. So magnitude of ay vector over magnitude of the a vector. And then you can see the magnitude of ay is equal to magnitude of a vector times cosine theta. In terms of vectors, we can write it as vector a times cosine theta. Similarly, if you look at the definition of the sine function, it's opposite over hypotenuse. The opposite in this case is the ax vector, or the magnitude of the ax vector over the magnitude of the a vector, and again you can solve for the magnitude of the ax vector and you'll get that as the magnitude of a vector times the sine angle, and then we can write vector ax as vector a times sine theta. So here you can see the ax and the ay components, their sine and cosine terms have interchange. So always when you try to find the component vectors, try to look where the angle is. Is the angle relative to the x-axis or is it relative to the y-axis? Depending on that, the components will either have the cosine term or the sine term. So that's a very important thing to note, because again people think that always if it's the x component you'll get the cosine term. If it's the y component, then it's the sine term. Not necessarily. That's why you always have to look at where is the angle. Is it relative to the x-axis or relative to the y-axis? In this case, as I have shown you, when the angle is measured relative to the y-axis, the components, their sine and cosine terms interchange. Another important thing is that the x and y axes does not need to be horizontal and vertical all the time. For example, here you can see an x axis and a y axis that has been slightly rotated in a counterclockwise sense. So the dashed lines shows you our usual x coordinate, x-axis and the y-axis, but the new x and y-axis has been rotated counterclockwise with respect to that. But still you can identify the angle, you have a vector. So let's try to apply the steps that I told you in order to find the perpendicular vector components. So you can see the positive x-axis is over there, the positive y-axis is over there. Then you can identify the angle that is measured respective to the x-axis, and then you have the vector A. So now what you're doing is that you are going to put the magnitude of the vector A as the hypotenuse of a right angle triangle and then construct the perpendicular vector components as sides of that right angle triangle. So for example, in this case, the sides would be like this. So that means a component vector in that direction, and then the component vector in the y direction, in the positive y direction. So if you recall, I am pretty much applying the head to tail method to construct this A vector. So the components, then I am going to label them, this one as AX component, and this one, since it is parallel to the y-axis, I'll call it the AY vector component. Okay, and always remember the vector sum of AX vector and the AY vector will always equal this original vector. Now again we can use the trigonometric functions or ratios to figure out AX and AY. So if I use sine theta, you can see that's equal to the magnitude of the AY component over the A component. So that gives me the magnitude of AY vector is equal to magnitude of A vector times sine theta. Now if you want to represent AY as a vector without the magnitude, then it would be AY equals A vector times sine theta. Now it's a positive sign because you can see the vector AY is in the positive y direction. Similarly, cosine theta, magnitude of AX vector over magnitude of the A vector, and you are going to get that the magnitude of the AX vector is equal to magnitude of the A vector. This time it's going to be cosine theta. And again, if you want to represent it as simply as a vector, it would be vector A times cosine theta. Again, here you'll see that it's along the positive x direction, this component vector over here. So that means it's a positive sign in front of the right hand side, which I'm not going to put in both cases. But still, I mean, the important thing it does not, x and y axes does not need to be always horizontal and vertical. They can be rotated clockwise or counterclockwise, but still you can apply that method I told you. First, identify the coordinates, whether they are positive or negative. Identify the angle, whether it's relative to the x-axis or relative to the y-axis. Then use the vector, the magnitude of the vector, as the hypotenuse of a right angle triangle, and construct the component vectors as the sides of that right angle triangle. So that's what you need to do all the time if you want to find the perpendicular vector components. Now let's try to do an example related to this particular idea. For example, here we have the positive x-axis, then the positive y-axis. But now there's no angle defined relative to either the x-axis or the y-axis. But there's an angle given that's like the angle between the positive x-axis and the horizontal line. The dashed line represents the horizontal line, and the angle is alpha. So this symbol is called alpha. Now how are we going to find the angle? How do we define the angle relative to the vector given, which is a vector? So if you can see, this a vector is vertical. So that means over here we have a 90-degree angle. So if this is alpha, that means this is 90 minus alpha. And then if you look at the xy coordinate system, the x-axis and y-axis by definition are perpendicular to one another. So that means this angle is also, you can see, it's alpha, because alpha plus 90 minus alpha should equal 90 degrees. So this is 90 degrees. So then what I'm going to do is that I can identify the vector over here, and you can see the angle is over here. But now the direction of the vector is reversed. This is not the usual vector that we have seen previously, where the vector tail is always at O, but here it's the head of the vector. But it's still fine. We can identify the right angle triangle like this. So you start from here, and your first side represents a vector parallel to the x-axis, like that. So that's the first vector. And then the other vector will be parallel to the y-axis. But now you can see their directions are different. So let me label this ax vector because it's parallel to the x-axis. Then this is the ay vector because it's parallel to the y-axis. But you can see it's actually in the negative direction. It's along the negative x-axis and the negative y-axis. So when I write down the expressions for the component vectors, I need to put the negative sign. So now let's look at the sine alpha first. Sine alpha is opposite over hypotenuse. So the magnitude of the opposite is ax vector, magnitude of the ax vector over magnitude of the a vector. And from here, you are going to get magnitude of the ax vector is equal to magnitude of the a vector times sine alpha. Now, if you want to represent this as a vector, remember to put the negative sign because you can see this direction is where we measure positive. This is positive. However, the ax vector is in the reverse direction. It's pointing in the reverse direction. So that's why I need to put the negative sign. So negative a times sine alpha. So that gives you the ax vector for this particular example. Next one, I'm going to define cosine alpha. So cosine alpha is the adjacent side divided by the hypotenuse. So the adjacent in this case is the magnitude of the AY vector over magnitude of the A vector. So again I get magnitude of the AY vector is equal to magnitude of the A vector times cosine alpha. Now if I want to represent the actual vector AY, you can see the positive values are measured in this direction for the y-axis, but the actual AY vector is pointing in the reverse direction. So then I need to put that negative sign. So vector A cosine alpha. So that's how you do this. Always go with that particular step. Identify the x and y directions, which directions are positive. Identify the angle between the vector and whether it's relative to the y-axis or the x-axis, and then construct the right angle triangle where you keep the magnitude of the vector as the hypotenuse, and then the perpendicular sides will give you this perpendicular vector components. So that's how you do this, and I believe with this you should be more confident in finding out the perpendicular vector components given any type of vector and any type of coordinate system, perpendicular coordinate system, whether they are rotated or not. You should be able to figure out the perpendicular components of a given vector. So this covers skill 1. Now let's talk about skill number 2, finding resultant vector from perpendicular vector components. Resultant vector is usually denoted by the letter R, and it represents a single vector that can describe two or more vectors. That's what is meant by a resultant vector. So when you are asked to determine the resultant vector or any other vector, you need to find two things. First one, find the magnitude, or what we call the size of the vector, and the second one, direction of that vector. So in this part, we are going to do that. We are going to find the resultant, the magnitude of the resultant vector, and the direction of the resultant vector. So in this example, we have just one pair of perpendicular vector components, ax vector that is along the positive x direction, and the ay vector which is along the positive y direction. So how are we going to find the resultant vector? If you remember vector sums, R vector can be easily written as the vector sum of ax vector and ay vector. Now, vector sum means we can put these component vectors as the sides of a triangle, a right angle triangle, because these two vectors are perpendicular to one another. So we can put them in a right angle triangle. So I'm going to use the graphical method where I'm going to slide these vectors. So let me slide ax vector to a position like over here, and that's my ax vector. And then I'm going to slide the ay vector such that its tail nicely fits the head of the ax vector. So like that. So that's my ay vector. So let me label these vectors ax vector and ay vector. And then the free ends, when you connect the free ends, that's going to give you the magnitude or the size of the resultant vector. Like that. And that's my resultant vector. And you can see, so looking at the right angle triangle over here, it's clear that this is valid, this relationship is valid. But the objective here is to find some sort of a expression, a symbolic expression for the size of the resultant vector and the direction of the resultant vector. So let me define this angle as theta. And that gives you the direction relative to the positive x-axis, because if you extend this line, that gives you the positive x-axis. So suppose that the resultant vector makes an angle theta with the positive x-axis, and then our objective is to find this theta and the length of this r vector. For that we can use trigonometric function. So that's why this method is related to the trigonometric method. You can see the right angle triangle. You already know these two sides because these will be given in a problem. How do you find the third side? You can use Pythagorean theorem for that, where the square of r side or r is equal to the sum of the squares of the other two sides. Like this. So then if you are solving for just the magnitude of r, that is equal to the square root of ax vector, the magnitude of ax vector squared plus the magnitude of the ay vector squared. So remember, this is a very important relationship. So that's why I'm going to box it like this. So we figured out the size or the magnitude. Now comes, how do we figure out the direction or this angle theta? Again, we can use trigonometric functions for that. You can see the easiest way is look at the opposite side and the adjacent. If you recall the trigonometric functions, the way we define those things in video 1, tangent of theta can be defined as the magnitude of the opposite side over the magnitude of the adjacent side. And then I can solve for theta by taking the inverse tangent on both sides. So if I take the inverse tangent on the left hand side, I'll simply get theta. And on the right hand side, I'll get inverse tangent of this ratio. That is ay, magnitude of ay over magnitude of ax. So that's the second important relationship for this scale. So pretty much this is what you're going to do in this part. You are trying to find the magnitude of the resultant vector and you are trying to find its angle relative to a particular axis. Usually it's relative to the x-axis, and that's why I figured it out as theta. Now remember, theta can be figured out in two other ways, right? It's not only the tangent that you can use, you can even use the cosine of theta. You can use the sine of theta to simply figure out the angle. You can try that out and you'll see you're going to get the same angle. However, traditionally we use the definition of the tangent theta to figure out this angle. Okay, let's try example number 4. We have to find the resultant vector of the given perpendicular vector components. Now remember, these are forces. So this is a force. That's why you have the units of newtons. 4 newtons in the positive y direction, and then there's a force, 3 newtons in the positive x direction. Remember, forces are also vectors, and we will be dealing with forces most of the time in this course. So that's why I got this example. So how do we find the resultant vector using the previous explanation? What I'm going to do is that I'm going to draw the two vectors head to tail in their head to tail arrangement. So we have the 3 Newton vector like that, And keep in mind that I'm not drawing these things into according to a certain scale. And then the 4 Newton vector like that. And then I will get the resultant vector by connecting the free ends of this two vectors like that. So that's going to be my resultant vector. And then our objective is to figure out the magnitude and the angle of this resultant vector. So let me say the angle makes a theta degree with the positive x-axis. And here you can see these are the component vectors. That is 3 newtons in this direction to the right and 4 newtons in the upward direction. So I'm going to use the expression that we got for the magnitude of r. So if you recall, this is that expression. You have the magnitude of ax vector squared plus the magnitude of ay vector squared. So here you can see ax vector is the 3 Newton vector, and you are going to get the magnitude of that 3 Newton and square that. For the ay vector, it's the 4 newtons in the upward direction. You're going to get the magnitude of that and square that. So the magnitudes are just 3 and 4. So you have 3 squared plus 4 squared, and this should equal the square root of 25. So it is straightforward that the magnitude of the resultant vector is equal to 5 newtons. So we got one part of the question, that is, we figured out the magnitude of the resultant vector. Now let's figure out the angle that it makes with the positive x-axis, and that is theta. So again, I'm going back to what we learned in the previous slide. We learned that theta is equal to inverse tangent magnitude of the y component, that is ay, magnitude of that, over the magnitude of the x component. So now I'm going to make the substitution. Inverse tangent magnitude of the ay component is simply 4. Magnitude of the x component or ax component is simply 3. And then when you do the math here, you are going to get that theta is equal to 53.13 degrees. So that's the answer to the second part. So we figured out the magnitude of the resultant vector as well as the angle it makes with the positive x-axis. So here this is with respect to the positive x-axis. So that's how you do this example problem. It's a very straightforward, simple one. Now let's try to apply skill 1 that we learned earlier and skill 2 together to find the vector sum of several vectors. So example number 5 is related to that. We are given several vectors and we want to find the resultant vector that describes all these vectors. As I told you, the resultant vector is a single vector that replaces a whole combination of different types of vectors. And this will be something very important in our course. Throughout the course, you will learn about these resultant vectors. So we have a 2 Newton vector in the negative y direction. That's a force, so that's why there's a unit n. So these are forces. This is a force. Then there's a 4 Newton force in the positive x direction. That's again a force. And then there's a 3 Newton force that makes a 45-degree angle with the positive x-axis, and the 3 Newton force is in the first quadrant. That's also a force. So now how are we going to find the resultant vector in this case? The first thing I'm going to do, I'm going to resolve this 3 Newton force to its perpendicular components, that is its components along the x-axis and the component along the y-axis. So that's the first thing I'm going to do. Let me separate out the 3 Newton vector like this, and then I'm going to consider its components. So there's going to be a component in the x direction and a component in the y direction. So this is the component along the x direction. And then this is the component along the y direction. And then this is our 3 Newton vector. And let's say that this is the component along the x direction, and then this is the component along the y direction. And this angle, as you can see, it's 45 degrees. Now in such a case, how do we find the ax component and the ay component? So we already did this several times. So I'm going to directly write down the components now. The ax vector component is 3 newtons times the cosine of 45 degrees. And then we have to put the units newtons. Since it is along the positive x direction, it's positive. Similarly, the vector ay, or the component along the y direction, that is 3, the value of the vector, times the sine of the angle, sine 45 degrees. And since this is a force, we need to put the SI units newtons over there. Now we have resolved the 3 Newton vector into its x and y components. With this, all that remains are the vectors that are either parallel to the x-axis or parallel to the y-axis. So this is where we have applied skill number 1, that is, given a vector, finding its perpendicular vector components. In this case, vector components along the x direction and vector components along the y direction. Now then you might question, how about this 2 Newton force and 4 Newton force? Do we need to find perpendicular components for those two forces? No, because you can see the 2 Newton force in this case is along the y direction. It's actually pointing towards the negative y direction. The 4 Newton force is pointing towards the positive x direction. So they are already parallel to the x-axis or parallel to the y-axis. So we don't need to worry about those two. What we need to worry are the vectors that are at an angle with the x-axis or with the y-axis. That's where we need to decompose those vectors into their x component vectors and y component vectors. Now at this point, I am ready to sum up all the vector components that are along the x direction and all the vector components that are along the y direction. Now let's define our x vector as the sum of all the vectors along the x direction. So what are the vectors along the x direction? We have a 4 Newton vector, so I'll put plus 4, and then the x component of the 3 Newton vector, which is this one, plus 3 times cosine 45 degrees. And remember to put the units, that is newtons. And then when you simplify this, you should get 1.62 newtons. And that vector is along the positive x direction. So that's why it's a positive value. Similarly, I'm going to define our y vector, that represents all the vectors along the y direction. So again, we have a component of the 3 Newton vector. So plus 3 sine 45 degrees. So that's this one, what we called AY vector. And then the 2 Newton vector, you can see it's pointing in the opposite direction, in the reverse direction. So as a result, I need to put that negative sign, -2, because it's pointing in the negative y direction. And then put the Newton to represent the units, and when you simplify this, you should get 0.12 Newton. Again, it tells you the total, the sum of all the vectors in the y direction is positive. That means it points in the positive y direction. Now let's put those resultant vector components on this xy coordinate system. So we had Rx vector as 6.12 newtons. So this is again not to scale, but I'm doing my best to give you a good idea about these vectors. And then we have the Ry vector that was at 0.12 newtons, and I'm again using the head to tail method. So the Ry vector will start here pointing upward like that, and that would be the Ry vector. So let me label those vectors now. So this is Rx vector, and this would be my Ry vector, and the size and the direction of the resultant vector is given by connecting the free ends of the Rx vector and the Ry vector like that. So the red arrow gives you the size and the direction of the resultant vector. So this would be our R vector. Now we are not done yet, because we need to find numerically what is the size of the resultant vector and what's its angle relative to the positive x-axis. So let me call this angle theta, and I'm going to use the previously discussed trigonometric techniques to find those things. So again, the magnitude of the resultant vector, or the size, is given by the Pythagorean theorem, or if you recall this expression, absolute value is equal to square root of the Rx component squared plus the Ry component squared. So solving this would give us the magnitude of the resultant vector, and then theta is equal to the inverse tangent of Ry vector, the magnitude of that, over the Rx vector. So now we can substitute the values. Here I'll have 6.12 squared plus 0.12 squared, and this is again, it's going to be 6.121 newtons. So that's up to 4 significant figures. Because like if you round this to 3 significant figures, you are going to get 1.62, which is the same value. So that means the more dominant component is the Rx component, whereas Ry component is extremely small. So that's why I told you this vector representation is not to scale, because this Ry component is very small, and that should be clear when we figure out theta. It should be a very small value where this R vector is almost parallel to the x-axis, and we should be able to get that when we substitute the numerical values over here. So numerator would be 0.12 divided by 6.12, and then when you solve this, you are going to get theta equals 1.12 degrees. So you can see it's a very small angle. The resultant is almost equal to the x the total sum of the x components, and it's almost along the x-axis, that means parallel to the x-axis. However, this is how you do such a problem, combining skill 1 and skill 2 to find the vector sum of a combination of vectors. Now, even though I explained this step by step, you should be able to practice this and do it very quickly. So this is example number 6. You can see there are 8 force vectors acting on the origin. Some of the force vectors are pointing into the origin. Some of the forces are pointing out of the origin. So we need to find the vector sum of all these forces. That means find the magnitude of the resultant force and find the angle the resultant force makes with the positive x-axis. So at this time, I would suggest pausing the video and try to do the problem by yourself. Now, this example looks complicated because we have 8 vectors in this coordinate system. However, if you look closely, you can really simplify the problem. Now, I'll point out this 5 Newton vector over here. You can see the 5 Newton vector is pointing towards the origin, and then this 5 Newton vector is in the reverse direction. It's again pointing towards the origin, but it's in the reverse direction. So I mentioned that these sort of vectors are called opposite vectors, and they will cancel out. So this vector will cancel out with this vector because they are equal in size and opposite in direction. Now, similarly, we can talk about this horizontal vectors. The 6 Newton vector is to the right and the 3 Newton vector is to the left. So if you think about tug of war, it's like 6 Newtons is larger than the 3 Newtons. So you are going to have a 3 Newton force, a net force of 3 Newtons to the right. So similarly, you can look at the vertical vector components, that is along the y direction. The 5 Newton force is downward and the 3 Newton force is upward. So there's a net effect of 2 Newtons in the downward direction. Now you'll come to the last pair. There's a 2 Newton force over here. So that is in this direction. And then there's a 7 Newton force over here. Again, if you look at the net result is 5 Newtons towards this 7 Newton force. So as a result, you can simplify this 8 vector combination into just 3 vectors. So let me draw those 3 vectors now. We have firstly the horizontal vectors. We have 3 Newton force to the right because this cancels out, and that I'm going to represent that by this arrow. So that is the 3 Newton force. And then vertically we have 2 Newtons downward direction, like this. So that's the 2 Newton vector. And then the 5 Newton cancels out, opposite vectors. There's a 2 Newton in this direction and 7 Newtons over there, making 45-degree angle with the horizontal. The net would be 5 Newtons making 45 degrees with the horizontal in this direction. So it's going to be like that. Something close to that. So now you can see we have decomposed, we have simplified our vectors. We have 5 Newtons over here, 2 Newtons over here, and 3 Newtons over here. And this angle, you should clearly see that's the same 45-degree angle. You can see without doing any sort of mathematics, simply by looking at the vector combination or force combination in this case, you can simplify the system. So we continue example 6, As you can see, we have simplified the problem into three vectors. The 3 Newton vector is already along the positive x-axis. The 2 Newton vector is already along the negative y-axis. The only vector that we need to decompose into perpendicular components is this 5 Newton vector. Now, I'm not going to draw the right angle triangle for as a guide, because you should be able to, by now, you should be able to do it mentally without even drawing the right angle triangle. That is finding the perpendicular components of this 5 Newton vector. As a result, I'm directly going to write down the components. First, I'll define the x component of the resultant vector as Rx. So this is Rx vector. You can see the 3 Newton force is along the positive x direction. So I have plus 3 as a result. Then the only other component in the horizontal direction is this 5 Newton contribution from the 5 Newton, that is 5 cosine 45. But you can see that's in the negative x direction. As a result, I'm going to put negative 5 times cosine 45. And then I'm going to put newtons because we are dealing with forces. And then when you simplify this, you are going to get minus 0.54 newtons. Similarly, I'm going to find the resultant vector component in the y direction, that is Ry vector. And again, upward is the positive direction. You can see there's no contribution, no vector in the positive y direction. There's a vector in the negative y direction, that is 2 newtons. So I'm going to put minus 2. And then the contribution from the 5 newtons along the y-axis. Again, it's pointing in the negative y direction. So I'm going to put minus 5 sine 45 and then newtons. So when you simplify this, you are going to get minus 5.54 newtons. So if we draw these two components on this coordinate system, you'll see that there's going to be a contribution along the negative x-axis like this. So I'll call that the Rx component. And then there's going to be a contribution in the negative Ry direction. So that's going to be a much larger, like that. And that's my Ry vector. And then you can figure out the resultant vector, which is pointing in this direction. So you simply connect the free ends of the two vectors and you should get the resultant vector. So that's the resultant vector, and let me call that R vector. And if this angle is theta measured from the x-axis, we should be able to now find the magnitude of R and the angle theta. Now finally we are ready to apply the expressions and figure out some numbers. So the magnitude of the resultant vector, as you know, can be obtained by taking the square root of Rx squared, the magnitude squared, plus Ry vector squared. So if we substitute the values here, we know that Rx value is minus 0.54 minus 0.54. So I'm going to square that, and then the x part is minus 5, y part, that is minus 5.54 squared. So if you do the calculation here, you are going to get 5.57 newtons as the magnitude of the resultant vector. And this is up to 3 sig figs. Now to get the angle, so let's try to calculate theta. Theta is given as the inverse tangent of magnitude of our y vector over magnitude of the r x vector. So that means we have to get the inverse tangent of magnitude of ry is simply the number without the sign. So I can put 5.54 over, instead of minus 0.54, I can simply put 0.54, and when you do the math here, you are going to get 84.4 degrees. That is again to 3 sig figs. But this is not what I asked initially. I asked you to find the angle with respect to the positive x-axis. So this angle is measured with respect to the negative x-axis. So that means we need to add this entire angle to theta. So that means we need to add 180 degrees to the angle so that the angle is measured from the positive x-axis. So angle from the positive x-axis simply I'm going to add 180 degrees to this theta value, and then for 3 sig figs you are going to get 264 degrees, that is up to 3 sig figs. So that's how you do this particular problem. This is the magnitude of the net force or the resultant force, and then this is the angle it makes relative to the positive x-axis. So my suggestion is try to practice this problem again, try to do it multiple times so that you really understand how to simplify these problems where you have multiple vectors. It could be forces or velocities, displacement, whatever vector. You have a combination and you need to simplify that to a resultant vector, just one vector. And this is the method to do that in terms of the trigonometric method. Sometimes instead of finding the resultant vector of many vectors, you might just get 2 vectors and you are asked to find the resultant vector. So here I'm going to show you a very quick and an easy way to find the resultant vector if only 2 vectors are given. So let's look at this diagram. You can see an A vector and a B vector. The angle between the 2 vectors is theta. Now here the 2 vectors are connected tail to tail. Both vectors, their tails are connected in this case, and the angle is with respect to those tails. Now this analysis is valid if heads of the 2 vectors are connected. So for example, like this, let's say you have vector A like this. That's your vector A, and then we have vector B like that. So now instead of tail to tail, the heads are connected. So this is our vector A, and then this is our vector B, and again this angle over here would be theta. So either way, like if 2 vectors are given, if they are connected tail to tail or head to head, then this analysis is valid. And also the other thing is that this theta, the angle between the 2 vectors, should be less than 180 degrees and greater than 0 degrees. So remember, theta should be between 0 and 180 degrees. So that's when we can use this method. So how do we find the resultant vector. So let me draw the resultant vector. Let's say over here the resultant vector is like this, and then we need to find its magnitude and its direction. So let me call it the R vector. So I'm going to show you how to find the magnitude and the angle it makes with the A vector. So remember, it's not with the x-axis or the y-axis. This method gives you a way to find the angle with respect to the A vector. So that means this angle. Let me call that alpha. Instead of our usual theta, let me call that alpha. So alpha angle is measured with respect to the A vector. It's not with the x-axis or the y-axis. So keep that in mind. That's a very important point. So now these are the equations that you can use. The magnitude of the resultant vector is given as the square root of A vector squared plus B vector squared plus 2 times the magnitude of the A vector multiplied by the magnitude of the B vector and multiplied by the cosine of the angle between the A vector and the B vector. So this is how you get the result, magnitude of the resultant. Then the angle alpha that the resultant vector makes with the A vector is given as inverse tangent magnitude of the B vector times sine theta divided by the magnitude of the A vector plus magnitude of the B vector times cosine theta. So I'm not going to derive how to get this expression, but it can be derived. Simply, we can use these results to find the resultant if we are given two vectors. So now I'll explain this using an example. So in this example, let's try to apply that quick method to find the resultant vector when two vectors are given. The important thing here is that this 2 Newton vector is along the x-axis. Now it does not need to be the case. However, this is a special situation where this 2 Newton vector is along the x-axis. I'm going to consider 2 Newton vector as my A vector and the 5 Newton vector as my B vector, and then this angle 60 degrees as theta. And then I'm going to substitute these values in that equation, in that expression. First, the expression is for the magnitude of the resultant vector. So that means square root of A vector squared. So this is my A vector squared. So 2 squared plus B vector squared, that is 5 squared, plus 2 times magnitude of the A vector, which is 2, times magnitude of the B vector, which is 5, times the cosine of the angle, which is in this case cosine 60 degrees. So now we can simplify this. So if you simplify this, you are going to get 4 plus 25 plus here you have 20 times cosine 60 degrees. Now you should be able to substitute for cosine 60 degrees and simplify this. So then you are going to get square root of 39 newtons, because you can see these vectors are forces. So the resultant magnitude should be quantified in terms of the units for force, which is newtons. So I can further simplify the square root. So then I'll have the magnitude of the resultant vector as, so it's going to be 6.24 newtons. 6.24 newtons up to 3 significant figures. Now I'm going to find alpha, the angle the resultant going to make with the 2 Newton vector. However, in this case, it is also the angle the resultant makes with the x-axis, because 2 newtons is along the x-axis. So alpha is equal to tangent inverse. I'm going to substitute the values. First, on the numerator, I'll have 5 times sine 60 degrees over 2 plus 5 times cosine 60 degrees. If you cannot remember this, then please look at the expression and make the substitution. And then when you simplify the numerator and the denominator, you are going to get inverse tangent 0.962. And then when you solve this, alpha, you would get 43.9 degrees up to 3 significant figures. So you can see this method is relatively quick if you know the expressions that needs to be substituted. So that's so I wanted to explain this quick method on how to find the resultant when you are given 2 vectors. Now there's another third method to find the vector sum, provided that you're given a combination of vectors. This is called the unit vector method. However, in our course, we are not going to talk about the unit vector method. But still, I would like to give you a brief explanation about unit vectors and how we actually sum up vectors. So unit vectors are vectors with magnitude 1, that is unity, and they pretty much gives you the direction. For example, in 3 dimension, you know there are 3 coordinates, like the x direction, the y direction, and the z direction. So these directions can be quantified using these unit vectors. Now this I hat, you can see there's a tiny hat, so this is a unit vector. This is actually the unit vector along the x direction. So j hat is the unit vector along the y direction. Actually, it should be the positive y direction. Is given by the j hat unit vector. The positive x direction is given by the I hat unit vector. The positive z direction is given by the k hat unit vector. Now, if you want to represent the negative x direction, then you will use negative I hat unit vector. So remember, unit vectors are used to define a certain direction in space. Now, how do we actually express a vector in terms of these unit vectors? Now, as you know, this blue arrow signifies the unit vector along the x direction. So that is our I hat unit vector. This unit vector is the j hat unit vector, and this unit vector is called the k hat unit vector. Now suppose that we have an object and that object moves in this 3-dimensional space. Let's say that it moves 2 units in the positive x direction. So it moves over here. So 2 units along the positive x direction. So I'll call that 2 here. And then the object moves 3 units along the positive y direction. So somewhere around here. So it moves 3 units along the positive y direction. So let's say at that point 3. And then finally it moves 1 unit along the positive z direction. So that is in this direction. Somewhere around that. So this would be the final position of that object. So it started from the origin, it moved 2 units in the positive x direction, 3 units in the positive z direction, and it moved finally 1 unit along the positive z direction. So that means relative to the origin, the final position of the object is over here. Now, when we connect the origin to the final position, we call that a position vector. So this vector is called the position vector. Okay, and then you can see the position vector has coordinates. The x coordinate would be 2, the y coordinate would be 3, and the z coordinate would be just 1 because it moved 1 unit along the positive z direction. So I need to put the coordinate somewhere here, like over here it should be 1. Okay, now how do we express this in unit vectors? Since each direction has its own unit vector, we can multiply the number of steps or the units that are moved in a direction with the unit vector corresponding to that direction and sum all those terms up. For example, if we call the position vector r vector, so r vector can be expressed as 2 units in the direction of x vector. So I have 2 times I hat plus then I have 3 units along the y direction. So we can write that as 3 times j hat, and finally 1 unit along the z direction or the positive z direction. So that's simply k hat, where I hat, j hat, k hat represents the unit vectors along the positive x direction, positive y direction, and positive z direction respectively. So this is how we express a vector in terms of its unit vectors. So you can see this is a 3-dimensional case. It's one of the cases you can have 2 dimensions. That means xy coordinate system is a 2-dimensional system. Then if you have a number line, then that's 1 dimension. You can express any point in terms of 1 coordinate. Okay, let's try out example number 8. We need to find the vector sum or the resultant vector for these 2 vectors. Now the special thing about these 2 vectors, they are expressed in terms of their unit vectors, I hat, j hat, and k hat. You can see A vector has I hat components, j hat components, and k hat components. But the B vector only has I hat components and k hat components. The j hat component is 0. So I'm going to rewrite B vector as 0 I hat minus 8 j hat minus 9 k hat, like that. And then the vector sum, usually it's given by the r vector, that is simply the a vector plus the b vector. So how do we find the vector sum? It's very easy. When we have unit vectors, we simply algebraically add the components of the corresponding unit vectors. So if it's the unit vector I, then we add the corresponding components in both vectors. So I have 3, And for b vector, it's 0, like that. Plus the corresponding components for the j hat. From A, I have -2. From B, I have -8. Finally, the components for the k hat unit vector. So from A, I have 5, and from B, I have -9. So then finally, I get the resultant vector as 3i minus 10j minus 4k. So that's the vector sum or the resultant vector of these two vectors A and B. Now finally, if you like, you can even find the magnitude of this resultant vector. So the magnitude of the resultant vector is given as the square root of the component in the I squared, the component of j vector squared, and then the component of the k vector squared. So like that. And then you would finally get the answer here. Square root of, you'll get 3 squared is 9, 4 squared 16, and then this would be 100 over here. So you will get 125, and then the answer here would be 11.2 up to 3 sig figs. So that's how you do this problem. It's relatively simple when compared to the geometric method and the trigonometric method. With that, we conclude the review on vectors. I believe the review done here is more than enough for our college physics course. Starting from video 4, my next video, we are really going to jump into physics concepts. So I will start video 4 by talking about motion, and specifically motion in one dimension. And I'll upload that video as soon as I can. Thank you.